Okay, so I have a poll at the end, or actually somewhere in the middle, and that's part of actually the discussion today. So we're going to conduct that. Again, this is not a democracy, so that you guys know. Everybody is going to participate, okay? You're going to tell me one way or the other, what do you think? And this is, you're not going to lose any points if you say one way or the other. And at the end, we agree into what is correct. Okay, so today we're doing the moment, basically the rotational motion. And let me share my screen first. Okay. For those who came late, I said hi earlier, okay? Anyway, before the recording. Anyway, so today we're doing rotational motion. Today is Tuesday, March 9th, okay? So we're going to explore the concept of circular motion. This is unlike the rectilinear motion or the motion in one line. This is motion that goes in circles. This motion requires at least 2 dimensions to imagine it or to conceive it or to work with it. Usually, actually in 3D makes more sense, especially when it comes to the concept of torque, okay? You will see that an object like this rod, for example, can be spin. I mean, you can spin it, okay, one way or the other. So that is what the concept of torque comes in here, and we will see exactly what that means in terms of force and where the force is applied, okay? Before that, I mentioned the rotational motion, rotational inertia, and that is similar to the mass in a sense, and that is the ability of an object to resist the change in its rotational state. Namely, if it was not rotating at all, the more rotational inertia you have, the harder it is for you to rotate it. Just like when you have a mass. When you have mass, the more of it, the harder for an object to move if it was not moving. If you have the object moving, it becomes harder for you to stop the object if it was not really, if it was moving, okay? So that's basically what the concept of inertia is in general, but in this case, it's related to the motion that is specific in this case, and that is a motion that goes in rotation around a certain axis, okay? So that is basically the key concept in here. We're going to explore the concept of center of mass and center of gravity. Those are related to one another. At least here on Earth, it's easy to find the center of mass using the force of gravity. Centripetal force, which is really not a real force, it's because real forces require interaction between 2 objects. This force is something that you experience while you're where an object is going basically around circles, okay? And the same thing, basically, centrifugal force is a force of inertia in this case, okay? That is the one that throw you outside of if you're turning, it's the one that pushes you outside. If you're going left, it's going to push you to the right, and so on and so forth. And this has to do with the velocity. The more velocity you have, the more of this force you're going to have. And then we're going to talk about rotating reference frames and what that means, okay? Similar to the gravity, basically, what that is when astronauts try to go, for example, in the before going there, they are trained in this this kind of environment to simulate the g-forces, so that when they are outside, actually they're experiencing that acceleration, if you wish, of the toward gaining more and more velocities. As a matter of fact, actually. But you can do it in rotation because, again, the same centripetal, in this case, acceleration, can be applied in this situation using the centrifuges, okay? Then we're going to talk about angular momentum and how important angular momentum is and its conservation. When there are no torques, the angular momentum is conserved, and that is this concept in here. It is the one that is responsible for the way most of the stellar systems look like. Basically, even the entire galaxy looks like it's a pancake, okay? It looks like it's flat, and the reason why is because of the conservation of this guy, angular momentum. And that is the reason why all of the planets, they're more or less on the same plane with the sun. And it's the same thing that you experience when you have a tub full of water, and then all of a sudden you pull the plug. Then in this case, the water starts to go. You will notice that the water that is closer to where the water is going, where the sink is going faster than the one that is going outside on the other side. And again, it's conservation of angular momentum. So this is a key concept in here. And if you take, for example, dough, like this is not really dough, but it's a material that is similar to it. And if you spin it faster and faster and faster, again, you're going to flatten it, okay? So that is the concept behind the all of these concepts that we're going to be exploring in this chapter, okay? So again, when an object turns about an internal axis, so you really need an axis of rotation, okay? It is undergoing a circular motion or rotation. Circular motion is characterized by two kinds of speeds, tangential speed and rotational speed, or in this case, sometimes called angular velocity, okay? So basically, this is what we're talking about. This is an object. Think of it as a tortilla, for example, okay? Not well-made tortilla, okay? This is the way probably I would have made it. Anyway, it's flat. So now if you take a point in it and fix it, so this point is fixed, so every other piece of it can spin as long as you can make it minimize the friction in here. So the only way for this it has to be a solid tortilla, okay? Because tortilla can tear, and that's not what I want. I want tortilla that doesn't, that is rigid. So forget about the tortilla. Let's say, for example, frisbee, okay? And make a hole somewhere and pass a rod in here so that that rod where the object can spin around it, okay? So in this case, it's going to go around that axis, okay? And the axis can be anywhere around it. So this is characterized by two things. For on any given point, this point, for example, and this point in here, they're moving around that axis with their own velocity. This is what we call a tangential velocity. If you were to stand in here, like on the merry-go-round, for example, you're going to be moving. You're going to be moving tangent to this circle, okay? This point has a lower radius, hence it has a lower velocity in this case, but it's moving nonetheless. An object that is in here need to catch up with that as long as it's rigid, okay? Because if I take a look at this axis in here, a point on this axis closer and points on this axis closer, a little later, this point would have moved in here, whereas this one has to go all the way here, whereas this one has to go all the way here. So the distance traveled by this furthest point must be greater than the distance traveled by this point. But both of them are traveling on the same axis, so they must arrive at the same time. Therefore, the tangential velocity in this case will be higher the further you are from the center of rotation. Whereas the angular velocity or the rotational velocity is how many angles would you cover per unit time. And that should be the same regardless of whether you're here or here or here, because you're sweeping the same angle at the same time, okay? This is actually the condition of rigidity. This is how I can tell this object is rigid or not. Because if this part is moving, describing a different angle than this one, for example, which did not catch up with it, so the angle in here, let's say, for example, it opened up at 45 degrees, this one barely made it to 30 degrees, then the distance between this point and this point before is less than the distance between it now and here, because it was right through this axis now tilted, okay? So this is a straight line. This is not the straight line between them. So now this has deformed, okay? So this is really how we describe rigid body motion. It has to be really rigid in order to understand. Again, when we're doing physics, we go always to the extremes, okay? So if somebody asks me, what happened to this body that doesn't look rigid at all when it's moving? Well, that has elasticity. So at this point, I'm not going to consider this one. I'm going to take makes bubbles in here. So that's what you heard. I'm going to take something that is rigid, like a rock, okay? I have a rock in here, okay? So a rock is probably a good description of it. So if I can puncture it and make an axis around it, that is what I was describing in here. Assume a rock is rigid by saying that this is not a potato, by the way, it's a rock, okay? So by saying every given point retain its distance with respect to the other one, no matter what happens to this object, okay? So that is what we mean by describing this motion here. Again, this is what I was talking about. The arc distance in here is a lot less than the arc distance in here, okay? You can clearly see, as long as the angle is the same, the this distance is less than that one. That means in the same amount of time. Let's say, for example, 1 second. Okay, if this one travels, let's say, for example, 1 centimeter, the other one could travel potentially 2 centimeters. So if I'm kind of considering the speed of the inner one is 1 centimeter times 10 to the negative 2 to make it in meters per second, divided by second. So its speed is 0.01 meter per second. Whereas the outer one is twice as much. This one will be, again, 2 times 10 to the negative 2 meters divided by 1 second, because both of them will go on the same axis. They were here, and now they are here. So the distance between them did not change. So this is a rigid body, okay? Then in this situation, that speed is twice as much, 0.02 meter per second, okay? Again, so if this is fast, the other one is twice as fast as long as the distance is in the radius, in this ratio. As a matter of fact, it's proportional to the radius, to how far we are from the center. An object sitting right on this point will not move. That is actually the definition of what this rotational motion. Every single point will move except the point where the axis of rotation passes through. That is actually a stationary point. That is actually a point that you fix. You bring nails on a rigid body and you nail it to the wall, make a little bit of frictionless contact in there, and the only thing you can do is spin it for a rigid body. You cannot, for example, it cannot travel, for example. Its center of mass would not be able to move, okay? So again, as I was saying before, rotational speed is the angle with which this is being described. Obviously, this angle here between these 2 points and the center of rotation is the same angle as this one and this one, because this is the same axis. So the angular velocity now in this case is the same, or the angular speed is the same. And usually in physics, we use the symbol omega. V is for the speed, for the normal speed, for the velocity. Omega is for the angular velocity. We use the letter omega for it, okay? Mathematically, they are related by this expression. We say the tangential speed, which is symbolized for it, V, is equal to R times omega. That's why if an object is at twice from the center of rotation, so if an object is right in the middle in here, it's going to move half as fast as this one. Because if this distance is R, but this distance is just R over 2, then the expression here, the omega is the same. For any given point in here, the angle has to be the same. Because if the angle is not the same as the object is rotating or spinning, then there is a deformation in the object. So it's no longer rigid. Okay, so it had to, in order for it to maintain its rigidity, that's the condition for it. Okay, so that is basically how we say it. And this is what you hear people talk when they're talking about the RPM. The car idles around, what, 800 RPM? That means 800 rotations per minute. That means that's how fast, basically, the engine basically turning the wheels inside. 800 rotations per minute, okay? You might be idling, you might be sitting because you have the brakes on, but the engine is still spinning, turning, okay? Now it says a ladybug sits halfway between the rotational axis and the outer edge of a turntable when the turntable has a rotational speed of 20 RPM, 20 rotations per minute, okay? And the bug has a tangential speed of 2 centimeters per second. So it's sitting right in the middle in here, and it's going with a tangential speed of 2 centimeters per second. What will be the rotational and angular and tangential speeds of her who sits at the outer edge? Well, if it moves at the outer edge, its speed will double. So it's no longer going to be 2 centimeters per second, but it's going to be 4 centimeters per second. And in here, it doesn't give you an option for how much its angular velocity, but it does not change. So the speed stays, the angular speed stays at 20 RPM. Does this make sense to you guys?
Yeah.
Okay, so that's basically the correct answer. Thank you. So the tangential speed, but they don't talk about because the question I was asking, the tangential speed, and the rotational speed. The rotational speed stays 20 RPM. Doesn't matter where you are on the disk, okay? Again, rotational inertia is an object rotating about an axis tends to remain rotating about the same axis at the same speed unless interfered with by an external influence, which we call a torque in this case, okay? Unless you stop it, okay? Either a friction which has a torque, or you hold it in place, applying a torque to it, or something like that. The property of an object to resist changes in its rotational state of motion is called rotational inertia. We use a symbol I for it, okay? The moment of inertia, sometimes we call it, okay? So it depends on mass of the object, how big the object is, and also the distribution of mass. The closer you are from the axis of rotation, the less moment of inertia you have. The further you are from the moment of inertia, the more inertia you have. That is basically in a nutshell, okay? It's unlike the mass, which only the inertia for the case of translation, for the case of rectilinear motion, you only have mass in that case. It doesn't depend where the mass is. In this case, it depends where the mass is. So here is the question for you. I'm gonna, before you answer it, I'm gonna first of all build the device and tell you exactly what I'm doing in here. So I have, let me remove this video thing in here. Background, let me remove the background because it's in the way right now. Okay, so what I have in here, oh, I need to remove this, sorry. Okay, so what I have in here, oh, let me stop sharing the screen so that you guys see better. So what I have in here is this, can I change this? Okay, good. So what I have in here is this object, which I'm going to basically spin it around it. So I have a big mass in here. Remember, everybody's going to participate. Everybody's going to vote, yes or no, okay? Vote on one side or the other. Here is the side of more mass. Here is the side of less mass, okay? So what I'm going to do is I'm going to put my finger in here and try to balance this one this way without actually, after I release this one. And I'm going to do the same thing while holding it this way, try to balance it also this way, okay? So both of them will give me whether or not I will be able to balance it or not. So here is where you guys come into play, okay? You're going to tell me which one, please, which one do you think is going to balance easier on, do you guys see the poll?
Yeah.
Okay, on this side, basically on the bottom side.
So whichever one's touching your finger.
Left, your right.
I'm sorry, this is the side of less mass. This is the side of more mass. Of course, I'm gonna release it from my left hand.
Is this gonna be a part of a discussion question?
Yes, it's gonna be part of the discussion question. And also there is a poll right now going on. So I want you guys to see the side of more mass is easier to balance or the side of less mass is easier to balance. So far, I have 9 of you thinking that it's the side, actually it's more, thinking the more mass, this way is easier to balance. Think of which one has more inertia, rotational inertia. Is it closer to the mass or is it away from the mass?
It's away from the mass.
Okay, vote, vote.
I already did.
So we still have few people who didn't vote, okay?
I can't unvote and rechange my vote now.
Okay, so I need more people to enter their vote, please, okay? So right now I'm missing 5 people. Everybody? Okay. So why did you say it's away from the mass? Okay, we're gonna stop the poll. Okay, guys, this is not a democracy. We still have 5 people who didn't, or at least 4 people who did not vote. Okay, let me take one person, because the vast majority believe it's easier to do it from here. Can one of you explain to me why it's easier to do it from here than from the other side? Any one of those.
I mean, I think it's easier. Well, in my opinion, it would be easier to balance if the mass was closer to the bottom of the finger, just because if the mass was at the top, wouldn't it make it disbalanced since all the mass is on the top and it'll pull the weight to the sides? At least that's the way I'm seeing it.
Okay.
Well, I thought about that. I thought about that too until you explained it, how when you hold it on top of your finger, and then if you think about it, if all of that is the same weight on the top, it would be easier to balance straight up because it's sitting up at the top and it's all the same like circumference and weight at the top, sitting at the top. And if your finger's straight and you stay balanced, then it would make sense for you that it would stay balanced at the top.
Oh, okay, makes sense why you said I can't retain my vote. Yeah, that does
you
make
know what
sense.
I'm saying? That's why I said I want to take my vote back.
You gave us a trick question,
It was a trick question.
so I
for
gave him a
sure.
trick answer.
Thank you, guys. That was a good explanation, everybody. Okay, so if I put my finger in here, the inertia is actually less because the mass is closer to the axis of rotation. This one will fall one way or the other, okay? So I will have hard time trying to balance it this way. Then if I do it this way will try to stay balanced more so than if I do it in the opposite direction, because the mass is far away from the distribution for where the center of rotation is. So it's going to spin one way or the other. You're right. I mean, ultimately it's going to fall because no matter how much I try, because I'm going to use my finger in here. So that is the item of the discussion today. So let's try it. So I'm going to focus on it. So this is one way. If you guys are actually, it fell quickly. So let's try it from the other side now and see if it's going to work. Try it at home. Okay.
It's a lot easier than the first time that you tried, though.
Absolutely.
You want a video?
No, actually, it's fine as long as you guys have fun with it. Okay. That's not even okay. That's fine.
I don't have
Okay.
play.
So I have everybody voting. That's good. Okay. So again, you can think of the baseball, basically, if you think of the baseball and how it's made. Thank you guys for participating, listen, and polling. And that's good. Okay. This is, by the way,
bat?
What?
You're talking about the bat.
Yeah, the bat. Yeah. So this is also works with the bat because the bat has a skinny side and has a big side where you actually hit the ball. Okay. And try to balance it, and you will see it's easier actually to balance it from the skinny side than from the big side. Okay. Have fun with this. Play with it. Okay. By the way, this tricks almost everybody who basically ask the question first before looking at the moment of inertia. Okay. So before looking at the slides in here. So this is the item of the discussion today. So what is the share thing? Share this. Meanwhile, let me put that background because I don't like this ugly background behind me in here. Okay, so hopefully you guys learned something from it, and that is how it's not just the mass did not change in this case situation. It stayed the same, absolutely the same amount, because it's the mass of this rod plus the plus that material there, which is made out of what? Cobalt. Okay, it's magnetic supposedly. But the point being in here is that the distribution. This is exactly what this point in here is. So the ballerina, when she's spinning, okay, and has her hands open, when she brings them down closer to her body, she's actually lowering her moment of inertia. She will spin faster that way. Okay? If she moves her hand, she's going to slow down. Okay? So that is exactly what the ballerina is doing. That is similar to it. So all of it is just a moment of inertia, which is something that masses don't do. Masses, for the linear motion, they don't have this, they cannot change their value. But in the case of rotation, you can change your inertia. And that's exactly what the ballerina does. She is spinning. All she has to do now is bring her hands closer. All of a sudden, she's spinning faster now because now her moment of inertia went down there is no external torque. So in this case, her angular velocity will increase. So we will see her spinning faster and faster. Of course, you guys probably have seen it in ice skating and all of those things. So they do that all the time, and they gain speed. And then when they open their arms or their body a little, the moment of inertia goes down. Okay. I'm sorry. Yeah, it goes up actually, which makes the velocity down. The angular velocity is down. So this guy is having a ball in here, going around in here and sinking because his moment of inertia, the mass is distributed very far away from the center of axis. So in this case, he's not going to fall one way or the other. It's easy for him to walk. Remove the stick from his hand, and you will see he's going to have difficulty doing it. Then he has to open his arms, and he has to use his arms. If he brings his arms closer to his body, it's going to be a nightmare. Okay? So walking the rope in here, these people, they learn about this chapter a lot. They study this chapter very carefully before going on that. Again, the moment of inertia depends not just on the mass, on how the mass is distributed, also depends on the axis of rotation. In this case, this pen has different moment of inertia. It has very little, if any at all, on this axis that passes through it because of the fact the mass is hardly away from it. Okay. In this case, when it's in the center, yes, you have mass that is distributed one way or the other, which is a lot bigger than this one, but it's still less than this one because there is a lot of mass in this case away from the center, from the axis of rotation. So the axis of rotation plays a major role. How far is the mass from the axis of rotation? To go back into my example earlier of the rod, the axis of rotation was just in the bottom, just exactly like this example in here. So it's like having it from this end. So this was going to spin this way, okay, or that way. So that was the axis of rotation. So that was similar to this situation, similar to this case. It's very hard for me to do this. I mean, it's actually easier because there is less moment of inertia because the mass distributed away from the axis that goes through so the center in here is very small. So in this case, the moment of inertia is very small. It's easy to roll this way, okay? And let go of it and it's easy to roll, okay? So that is, again, the rotation. Okay, again, the moment of inertia depends on a lot of factors. For a point particle, it's mathematically, if you're ever going to get an expression, most of the time will give you the value. So it's the mass times how far you are from the axis of rotation, if it's just a point charge, point mass. If it's a ring, like this one, the mass is equal to, the moment of inertia is equal to mr squared if it passes through its axis of symmetry. So think of a wheel, okay, a bike wheel, okay, and the axis of symmetry is just where the bike goes through. So that is, in this case, it's exactly like a point charge, point mass, mr squared, okay. But if I were to spin it on an axis on this side, then it's different. So again, it depends on the axis, how you want to spin this. This is not something that we can have. There is not anything similar to it when it comes to translation, rectilinear motion. Again, it's 1/3 of ml squared on one end of the rod, like the rod I was doing actually, plus m times the distance squared. So I'm assuming this has a mass. And if I can find the distance, I can find the moment of inertia. Now on the middle, it's equal to 1/12 of ml squared. Notice that in this case is less than that one because yes, there is mass away from the center of rotation, but it's not as much as in this case, okay? And in the case of a cylinder, or actually also a disc, or any of those shapes, it's always 1/2 of mr squared, okay? And finally, the solid sphere has this formula, 2/5 of mr squared. Don't worry about memorizing these numbers because you're not going to need to memorize them. If in case you have a problem, you're going to be given the formula, or you're going to be given the number on it, okay? But that to give you an idea how this is working in terms of the mass and how far is it, or how is it distributed around the axis of rotation, okay? Here is an example, and this is sometimes it's hard to quickly associate with. You have a hoop, which is like a ring, and you have a disc, which is full, okay? Both of them have the same mass. Both of them have the same radius. Which one would reach the ground first? Which one has less moment of inertia? Which one resists the change in motion more? If you look at this formula in here, it's going to tell you. This is basically the ring, and this is the disk, okay? Which one has more inertia, this one or that one? One of them is mr squared, because both of them have the same mass, the same radius. Okay, yeah, so it's the hoop. So it has more inertia. That means it's going to resist the change in rotation more so than this one, because both of them have the same mass. So their change in motion, the translation, because they do translate too. They move on this axis too. So both of them have the same translational inertia. They have the same mass. Both of them have the same radii. So in this case, the hoop will resist more and will arrive later versus this one, because this one has less inertia, so it's going to resist little, and it's going to come down faster. Make sense?
I think so.
Yeah, it does.
We used to do physics 11, at least when it's in parallel with physics 10, but this semester we had low enrollment in it. It was not offered. Hopefully in this the fall we will have it again. And we used to do this experiment. It's a lot of fun, basically. We have all kinds of disks and shapes, and we tried this and other things. But okay, it is what it is, okay? So again, it's the disk that is going to reach the ground first. Which one will reach the bottom first? It's the disk for the mentioned reasons. Again, to go along with the concept of rotational inertia and the concept of angular velocity, we have the concept of torque, okay? You have been fortunate enough to go on a different planet and another system, okay, where they have never heard of the door, and you invent a door for them, okay? Great, you put the door in there. And now you will tell them, okay, to go and put the knob somewhere. So here is the fixture. Here is the axis with which the door can rotate. Basically, this is the side of the door, okay? And you tell them, take the knob and put it, install it on the door. So where would be the best thing to put it? Is it here? Or here? Or here? Option 1, 2, and 3. 3, further away from the center axis of rotation, because in this case, if you put it in here, the door is not going to move because you're just on the axis of rotation. So if trying to push one way or the other, the door will not move. If you move it a little bit, it's going to have a little bit of effect, but not as much as position 3. Does this make sense? This is, we know it on Earth because we have doors, but on this planet they have never heard of a door. Okay, just basically told them how to build it, and you told them take this, make a knob, and put it on the door. So now they're confused. They're looking at you. Where am I going to put this one? So the correct answer is 3, because then you will have more effect in terms of rotation around this axis. Okay, great, they tell you. We understand you have to put it in here. Which way should we push it? Should we push it this way, or should we pull it this way, or should we push it at an angle this way, or how are we going to make this door open and close? Okay, so again, you have option 1, option 2, and option 3. Come the door handle and pull it this way. The door is this, okay? And you're trying to pull it this way. Is this going to help it rotate? Or you have to pull it this way? Is it this way? Do you pull doors?
No. What do you pull it towards yourself?
If you pull it towards yourself this way, I mean, like this I'm doing right now, you're trying to remove it. You're trying to yank it from its fixture. It's not going to spin one way or the other. If you push it this way, you're going to push it against the wall, and it's not going to move. So obviously this way or that way is easier. Okay. So again, this is the concept of torque. So what you're trying to tell them is, listen, guys, you need to apply torque. And a torque has to have an arm length. This is the arm length. The greater it is, the easier, the less force you will need to get the torque. Okay, that's one thing. Furthermore, this arm length and the direction of the force better be perpendicular to get the maximum effect from it. Okay, so that is what the concept of torque is. Okay, so you need an arm length, basically how far you can be from the axis of rotation. And also direction for the force has to be perpendicular to get the maximum effect. If it's not perpendicular, you're going to get an effect for rotation, but not as much if it's perpendicular. Now, if it is in the same direction as the arm length, you're not going to do anything. If you're trying to go with option 1, basically, you're trying to push the door into the wall. I mean, push it sideways, not even if this is the door. I'm trying to get something like, I have this one. Let's see if I can get this. This is a door. Oops, the other camera fell. That's fine. I'm not going to need it to. So this is a door, okay? So if you're trying to push it this way, you're trying to basically push it against the wall, or pull it this way, you're trying to pull it from the wall. Obviously, it's easy to do it this way or the other, okay? So this is, again, the concept of torque, okay? So the torque has this concept, lever arm times force. So you need the force still, okay? But you need the arm length of that force too. You need its arm to apply it. And the direction actually plays a role too, as you can clearly see, okay? So these people, they have no idea. I told them, okay, apply 10 Newton and it's gonna work. Oh, we did it. We applied 10 Newton. Nothing happens. The door stays in its place. Actually, it's yanking, it's coming out from its axis. They applied it in the wrong direction, okay? So where the force is applied, the direction in which it acts, that's important, okay? Here is a case. Obviously, this is an angle, but not as much as this angle. So now it's taking advantage of the full arm length, which is this one. So this is actually the arm length in this situation, which is in this right angle triangle. It's this side of the right angle triangle. In this situation, if you change the direction, it's going to go the whole hypotenuse of that triangle, which is the biggest side of any right angle triangle, is the hypotenuse. That's why 90-degree angle is the best, okay? Obviously, if you take the distance and make it longer, you're going to have better luck with it. You're going to have stronger torque. So if you take those big trucks or those trains that have this big bolts in them, and you would want to spin them enough so that you open them, obviously you need the very, very, very long, basically arm length, and you can, and it opens, okay? Or the left bit of force, and it opens and spins, okay? So that is basically how this, what this is talking. So that is the concept of torque. So if you ever hear people talk about torque, this is what they mean by it. That's exactly what the engine does, actually, because it wants to spin things. So whenever you're trying to spin something, you need a torque. As a matter of fact, let me give you an example where technically we have a problem. If I take an object in here that is fixed in the middle, and if I apply a force on it on one side and a force on it on the other side, let's say, for example, I apply 10 Newton in here and 10 Newton in here, this object is not going to change its location. It's not going to be here because the sum of the forces is 0. When sum of the forces is 0, its center of mass actually is not going to go anywhere. It's going to stay in its place. But this object clearly is going to spin because this one will help it spin clockwise and this one will help it spin clockwise. So both of them will have will help one another in making it spin. So there is a clockwise rotation in this case coming from these two forces. Each force times its distance is a torque 1. The other force times its the other distance is torque 2, and this object will spin. And the net torque in this case will be just the sum of these two torques. Both of them are doing the rotation. Because even if I don't do this, and as long as it's fixed somewhere in the middle, and if I apply the 10 Newton by itself, it's going to have a torque by itself. And if I don't do that and do the other one, it's going to have a torque by itself. So this object will spin in either case, okay? whether I have the 210 newtons and or only one of them. Obviously, if I only have one of them, I have half as much torque if I have two of them. That's the only difference. But both of them will cause this rotation clockwise in this case. This is how the clock goes. It goes like this. So this is a clockwise direction. Usually when we're doing rotations, clockwise is a negative number. So counterclockwise is positive. Doesn't matter about the size, but this is a convention, okay? So this is the second item in here of the discussion, and that is to recognize the positive direction of rotation. The positive direction of rotation is counterclockwise, the opposite of which way the clock goes. Make sense?
Can you repeat that?
Okay. Our second item of the discussion is to recognize the convention for positive rotation. Rotation is said to be positive if it is counterclockwise against the clock. Good? That is a convention. Okay? So in my case in here, this rotation, that example, is actually in the negative direction. Okay? Good? Everybody?
Yeah, that's good.
Okay, very good. Okay, here is an example. Suppose a girl on the left suddenly is handed a bag of apples weighing 50 Newton. Oh man, and these guys were in equilibrium, okay? Where should she sit in order to balance, assuming the boy does not move? So right now we're balanced. So basically, she's applying a torque right now, which is a positive torque, by the way, of, what is it? Whatever it is, it's 3 meters. Who cares about this? 5 meters and this 4 meters, okay? And right now we're going to add 50 Newton to the problem times 3 meters. So it's going to be 150 Newton meter, the new torque, okay? So that is basically the additional torque to this equation. So this boy needs to move back to minimize, to cancel this effect, basically, to add this, because he's applying a negative torque in this case. But since he's not moving, she needs to lower her torque. She needs to go back a little to make it back to wherever it was, okay? So that's basically where she's given 5 newtons. Why did I say there is missing information in this problem, okay? This question, we don't know the torque of the other two guys. Because we need to know the torque of the boy right now to find, so ignore this question for right now, okay? Because we need to know how much torque in here and what her current torque is in order for basically to balance it with the correct arm length of this force in here of 150 Newton. I mean, right now, if she takes it there, it's going to be 150 Newton meter. But if she takes 50 Newton, she needs to change her torque and that of this one to a new location in here to compensate for that one. So it's going to be 50 Newton times the distance she is going to move to, plus her own weight, times the distance that she needs to move back. This must be equal to basically how much the weight of the boy times the distance that the boy has, okay? So this is the equation that we need to solve. We need to solve for this x. we need to know her weight. We need to know this is the girl. We need to know the weight of the boy, and we need to know how far the boy is right now from this side in here. Okay, which is probably, if somebody is going to say, it's the weight of the girl times the distance of 3 meters. It's still, we need the weight of the girl. Okay, incomplete. Make sense? Okay. Probably if you read the question in the book, maybe it has more information than what we have in this slide.
Do we need to add 50 Newton with the weight of the girl, right?
Because she's carrying now 50 newtons of apple, 5 basically pounds, 5 kilograms of apple, 10 pounds of apples. Okay, you give it to her. So now it's her own weight, which was before in the past, plus the 50 Newton. But she needs to move to a point in here, closer or further, it doesn't matter, so that her torque now cancels the torque of the boy. And the boy's torque used to be, because he didn't move at all, it used to be the weight of the girl times whatever distance the girl is, which is 3 meters. So this is the equation that we need to solve in here. We need to find x, basically. That's what the problem is. We don't know x, but we don't know the weight of the girl. This is the weight of the girl too, because the weight of the girl times 3 is exactly the torque of this boy too, regardless of before we gave her the apples. So this is an incomplete question right now. And for some reason, they're saying probably she has 200 Newton. If you do that equation with 200 Newton, you're going to find the answer. Okay. But if it's not given to you, that's basically what this thing in here, the question is incomplete. I'm sorry about that. Okay. But she needs to move somewhere so that this equation still holds. At least conceptually. Do you guys understand the idea first? So if she has some more weight, she needs to move closer because the boy now needs to compensate for her torque, and that for the additional 50 Newton of apples. So for him, either he moves back, since he's staying in his place, because his weight, he cannot change it. The only thing he can change in this case is the location. Either he moves her back to have more torque to compensate for the torque of the girl plus the 50 Newton, or since he cannot move, stays in his place, then the girl must move actually closer. Make sense? To have less arm length, because now her combined weight now with the apples is more. Make sense to you guys? Yes or no?
Yeah.
Yep.
At least conceptually. I know the math in here is missing a piece of the puzzle to solve it, but that's basically in a nutshell what this thing is. Okay. So if we don't know the weight of the girl, we can intuitively say one of the two things must happen. Either the boy must move back, because now all of a sudden there is an additional weight applied on the same arm length, which is 3 meters. To have more arm length of his own, because his weight is not changed. He still has his own weight. So that is something to compensate for that. But since he cannot move, so his torque is fixed now, and it was whatever it was before to basically balance the girl. Now the girl must move closer to have less arm length because her force now has increased by that many newtons by her own carrying basically those apples. So now she needs to move closer to have less torque. Okay, so that's how you balance things. This is a pivot point somewhere in there. Okay, again, I mentioned several times the center of mass centrum is the average position of all of the masses that takes up the object. Center of gravity is the average position of weight distribution. This is true only when you are in the case of Earth, and they are both of them the same on Earth. So basically, you can take an object, suspend it from one end, and see. If it hangs this way, you know that the center of mass is somewhere on this axis. Somewhere on this axis. Take it and hang it from a different location. I'm trying to draw the same object, probably hanging it from here. So now the previous axis was this one, okay? Now the new axis is this one. So I know the center of mass exists somewhere where these two axes meet, or actually planes meet, and they meet in an axis by itself. So if I take it on a third axis, doesn't matter which, and basically suspend it. Now, previous axis were this one, and the other one. Now the third one probably will meet them somewhere. I did not draw it correctly in here. So that is actually where the center of mass is. okay? And the center of gravity in this case, because I'm using the weight as this, that mechanism. You have to understand something which is very, very critical. This is one of the few concepts that are pure mathematical concepts. They have really no, they're mathematical. They don't exist in reality. Let me explain. If I take this object, for example, box, and try to find its center of mass, it's probably somewhere in the middle in here, okay? If I go there with a microscope, I don't find anything in the center of mass. There is nothing in it. Okay, if you don't believe me, let's take another object in here that is made up of two similar objects. The center of mass is somewhere in the middle where there is actually no material whatsoever. So this has certain mass, but the center of mass is just a mathematical idea that helps us solve a lot of problems in physics, okay? Newton himself, when he arrived to his laws of gravity and explaining the motion and all of that, he stuck for 40 years trying to come up with an explanation. Why did he consider the distance between the Earth and the Moon versus the distance between the apple and the Earth, and the distance between the Earth and the apple? He didn't take it about 1 or 2 meters when the apple falls to the ground. He took it the radius of the Earth. And that means that as if the entire mass of the Earth is situated at its center of mass, or center of geometry in this case, which is center of mass. And for that, of course, he didn't have any tools at that time. He had to invent calculus, and that's how he basically arrived to the conclusion. So that's how he invented, basically he was doing physics, and also he invented a brand new branch of mathematics called calculus at that time. It seems like he was stuck doing everything by himself. Nobody was doing anything. So again, this is how you arrive at the center of mass in here, again, by hanging weights and seeing what it needs, and that is actually the idea behind it. And the condition of equilibrium is that somehow the center of mass must pass by a base of some sort, and that's why the Tower of Pisa did not fall. If this leans a little more, this center of mass will pass at some point by this critical point in the base, after which it's going to fall. So if the center of mass, for example, the axis through which passes through this point, that is too late for that thing. It's going to fall. Okay. So this is the condition of equilibrium, if you wish. The center of mass must stay in its location. When you walk, what you do actually, you lean forward. So what you're doing, you change your center of mass in such a way that now it doesn't pass through between your legs, between your body. It's actually outside. So what you do in this case, you move your foot to catch yourself before falling. And you do this one. So if you guys are getting into this branch of basically kinesiology or all of these things, you understand this. This is basically how motion is. So you always are in a state of falling when you move. So you move your body, just like the Tower of Pisa. You lean it forward if you're moving forward. And the center of mass is now outside of your base. So what you do in this case, you catch yourself before falling. Okay, you actually move your foot or the other in order for the center of mass to stay always inside your area in there. Okay, make sense?
Yep.
Okay. So again, any force directed toward the fixed point is called centripetal force. The only reason why this thing does not go anywhere is because the girl is holding it and expressing, exerting a force on the string, and the string is exerting a force on the bucket, which is probably full of water. But if somebody takes the string and cuts that one, that case, the centripetal force is not there, and the object will be subject to centrifugal force, which is really its inertia, that's all. Because its inertia will keep it moving in this direction away from that direction. So in this case, the centripetal force is really real, and in this sense, it's the force provided by a string on the bucket of water, whereas, and in here, it's actually the girl who's actually connected to the other side of the string, because all she has to do is let go, and then in this case, the bucket and everything else fly with it, okay? So centripetal means center seeking or toward the center. To whirl a tin can, at the end of a string, you pull the string toward the center and exert the centripetal force to keep the can from moving in a circular path. I mean, the can is trying to go away, actually, and you're holding it all the time. So it's actually falling towards you all the time, toward the center of rotation while it's moving, okay? The centripetal force is a force that must compensate for this inertia, which is a mass times the tangential. Remember that tangential speed that we talked about, V squared divided by the radius. So it's always the mass times the velocity squared divided by the radius. So even if you're not tethered to a string and you're rotating, spinning, because the car provides that centripetal force, moves you back, okay? So in this case, you're accelerated toward the side of the car with the velocity v squared over r, how fast the car is. If the car is taking the curve slowly, then there is very little force. If the car is going fast on the curve, you're going to feel it, okay? Actually, you would need as much wall or as much basically side of the car to keep you from flying. If you put something and hang it onto the rear view mirror, you're going to see that one actually lean one way if the car is turning this way, or this way if the car is turning to the other side. That is that quantity, v squared over r, okay? So on a road that turns, for example, this way, so engineers, what they do something to prevent cars from sliding. They put a lot of friction in here. They make the asphalt as much friction as possible to prevent the cars from sliding out, okay? And then also what they do, they tilt the roads a little. So they do what is called banking the road in here. That is really what civil engineers work on, trying to make sure that cars don't slide. And even though, depending on, of course, on the curvature, depending on the turn, how sharp the turn is, okay? And even though, so what they do, they go meticulously calculating the coefficient of friction with the ground, they calculate how much angle is in terms of the tilt and all of that, and they post a speed limit. If it is a very sharp turn, there is one in here in Redlands that is super sharp, and people don't really, they come in on Redlands Boulevard coming from Moreno Valley, and they see the sign from, if you don't really pay attention to it, it's a very dangerous turn. And it tells you 25 miles per hour. You really have to go that low to make the turn. Sometimes it's higher, 45 miles per hour, because this radius is very, very wide, relatively speaking, compared to 25 miles per hour. There is usually engineers that are tricky. They add a little bit of room for them. I mean, even if you go 47, 48, sometimes even 50, you may be able to make the turn, okay? Because they always lower it a little, okay, compared to that one. But this one, 25 miles per hour, if you're coming at 40 miles per hour, it's very dangerous, okay? So maybe 30, 27 miles per hour becomes critical in here. And it's because of that v squared, because of this number in here, z squared. So the more, especially in this case, the more dangerous it is. If it says 50 miles per hour, even if you go probably 55, you're going to be safe. Even if you go 57, probably you're going to be safe. 62 may be okay. But this one, so the difference of 12 miles probably will not make a lot of difference. But this one, if it says 25 miles per hour, if you go 5 miles above, it's going to make a big difference because of that square thing, okay? It's super dangerous. So that's exactly what I was talking about in here. So there is a center of curvature somewhere. So the engineers usually study how this one's, and they make the roads so that you can make the turn. And they post speed limits in there based on that. And usually there are two factors, as I said, the friction, basically the condition of the road itself. And of course, also if they can tilt it a little bit. Do you guys see the NASCAR race cars, basically when they're going on turns, they really make it banked as much as possible, but they're going at super speed, super high speeds. Did you see them or not? Anybody?
They delivered.
Not really.
Well, pay attention next time. At least the cyclists, the bicycles in the Olympics, they do that. They are actually tilted, okay? When they are on the stadium trying to go for the last few minutes and last few turns before getting to an end, okay? Okay, again, this is the 4 times as I was talking about, okay? Suppose you double the speed at which you round a bend on the curve, but what factor must be centripetal force changed to prevent you from skidding? Skidding, in this case, 4 times because of that square thing, okay? And this is again the radii. The centrifugal force is the one that I was talking about. It's not really force, it's an inertia, okay? Although centripetal force is centered toward occupants inside the car system seem to experience an outward force. This apparent outward force, and the key word in here that needs to be underlined is apparent, okay? Outward force is centrifugal force. Centrifugal means center fleeing or away from the center. It's just the force of inertia, really no more, okay? It is common misconception that a centrifugal force pulls outward an object. So there is no such a thing, it's just the inertia. The string breaks, the object doesn't move radially. It's going to move actually in this direction, okay? It continues along its path because no force acts on its Newton's first law of motion. This is it's not the real force, okay? Just basically the inertia of the object, keeping it in the same direction. Again, you can do this to simulate the force of gravity, okay? So as far as this object is experiencing a force in this case, if it doesn't see anything in there, and it calls this force as its mass times its velocity squared divided by r. So that's basically what it's, and you can make this value as big as g, which is 10.810 meter per second, or 9.8 meter per second. So if you have a big enough velocity and radius, you can still make that turn into simulate gravity, okay? So for astronauts, for example, on a long trip somewhere else, they can actually that's why you see a lot of sci-fi movies and they have those big spinning turns in there, because supposedly the astronauts are living in that station for a long time. So they really need to be adjusted to that gravity, at least to have some sort of a feel. Otherwise, they will lose muscles and they will have problems with that gravity there, okay? Still have about 20 minutes, we're good. So again, to simulate an acceleration due to gravity g, which is 10 meters per second, a space station must have a radius of about 1 kilometer in diameter and rotate the speed of about 1 revolution per minute. This is basically what you're going to do. You want 10 meters per second to be v squared over r. If r is 1 kilometer, so this is 10 to the power 3 meters, and the velocity needs to be 1 revolution per minute. So the velocity is 1 revolution per minute. That means 2 pi times the radius, which is 1,000, okay? So this is the circumference per minute, which is 60 seconds. Cancel the 60 with this number in here and do the math. 2 pi is roughly 60. 2 pi is roughly 6, I'm sorry. Cancel the 6, so it's going to be about, basically, what is it? 100 meter per second. You have to square this number. When you square the meter per second, it's going to be 10,000. 10,000 divided by 1,000, because you need the radius in the denominator. 10,000 divided by 1,000 is about 10. So if you can go 1 revolution per minute, this is slow, okay? 1 revolution per minute is super slow. So if you see them in the movies doing slow motion, that means because they have to have a huge radius of 1,000 meters. That's 1 kilometer. 1 kilometer is about 10 times the football stadium. That's a big station. If you cannot do that, if the station is a lot smaller than that, then it has to spin faster, okay? To simulate gravity, that's all. You need to spin faster. And actually, it's much easier to spin faster with less radius than to do it with the other one to compensate for that, okay? So at the end, you can do that. Mathematically, you can solve this problem, okay? So again, the angular momentum is the inertia of rotation of rotating objects is called angular momentum. No, actually, the angular momentum, I don't know what that is. Here is the definition for it. It's the rotational inertia times the angular velocity. This is similar to the linear momentum, which is mass times velocity, but I don't have mass now. I have actually rotational inertia or moment of inertia, the one I described in the first poll, okay? That is what we're talking about. And instead of velocity, we have angular velocity. So that's basically what this expression is. Symbolically, we write the angular momentum as L, the moment of inertia is I, the angular velocity is omega. Symbolically, we write the linear momentum as P, which is mass M times the velocity V. So V is like omega, M is like I, and P, linear momentum, is just like the angular momentum. This is what causes the planets to stay in their basically plane, okay, around the sun. Can be explained by the conservation of this quantity, okay? That this quantity doesn't change as long as there are no torques, just like the conservation of regular momentum when there are no forces. So these two ideas are similar, okay? Linear momentum has actually a lot of importance in terms of rotational motion, just as much the linear momentum has. So for example, the ballerina, when she brought her hands, she had an angular momentum before bringing her hands. She was moving with an omega 1 with her initial momentum I1. When she has her hands open, her moment of inertia now changes when she brings her hands closer. When she brings her hands closer, in this case, her moment of inertia went down because less mass now is away from the center of rotation. Actually, more of the mass is closer to her body now. So it's similar to the situation where I had the mass closer to this side and I tried to balance it. So she has less mass, less inertia. But then omega needs to go higher. Omega 2 needs to increase to compensate for the decrease in moment of inertia so that the total angular momentum stays the same, because there is no external torque. Nobody came in and pushed that ballerina faster or touched basically some of her hand or something to slow her down. So in this case, the only way, because there is no external torques, so the torque in this case is the angular momentum is conserved. So if she brings her hands closer, she needs to move faster so that this quantity doesn't change. The product of these two numbers don't change, okay? If she opens her hand in this case, she increases her moment of inertia, which means that she needs to move slower so that the product of these two numbers stay the same. Make sense?
Yes.
Yes? Okay. So again, it's for a point particle, it's the mass times the speed for the linear momentum. And for the motion that I was describing, it's I times omega, okay? So an object or system of objects will maintain its angular momentum unless acted upon by an external net torque. This is similar to the second law of Newton, which is basically the change in this case of the angular momentum is proportional in this case to the net torque. If the net torque is 0, then L needs to stay the same, constant, which we call it in this case conserved quantity, okay? And all of these are examples. Basically, when you double the distance, what is it? Suppose you have swirling, can you a can around your hand, suddenly you decide to pull the rope in halfway, but y factor, the speed of the thing changes, okay? So if you bring it halfway in this case, remember, we did that earlier. We said that the speed is equal to omega times r. So if you bring it halfway in this case, and you maintain the speed in this case, so I'm sorry, by what factor the speed of the can changes? Okay, if the angular momentum stays the same, as long as there are no external torques in this case. So if you bring the mass halfway, its angular velocity needs to go faster now by a factor of double, because again, the distance changed now, okay? The mass is less further away from the other one, so now the distance is the angular velocity doubles in this case, again, because of the angular momentum conservation. So again, the law of conservation of angular momentum says, so with no external torques, net action on a system, the angular momentum of that system remains constant. That's what we call conservation in this case. Okay, it's not changing. Analogous to the law of conservation of linear momentum. If no external forces act on a system, the total linear momentum of the system remains the same. So this is identical to that one. Okay, this is the example I've been mentioning all along. In this case, this guy has a high I, less omega. When he brings his hand closer, his I becomes smaller and omega becomes dizzying. In this case, becomes higher and higher. I tried to do this one. Actually, we have this one in the lab. Tried to do it, and honestly, I get dizzy. So I cannot do it anymore because I think when you become a little older, it becomes dizzying, truly. Okay, omega becomes very high. Okay, again, this example is coming from that one. So if you double I, omega will go by a factor of half. If you half I, omega doubles. Okay. So that is really the whole idea behind it. Okay. So this is chapter 8 for you guys. I had internet problems all day today. You guys were lucky. Today Spectrum actually had no internet for our neighborhood since noon until like around 2 o'clock before they fixed it. Okay. So hopefully this problem doesn't happen. And if it does, I will let you know. And I will try to use my phone to communicate with you guys, because I don't think I tried actually to do in the past with my phone, basically to do a lecture like this one. It did not work. So if that happens, I will let you know ahead of time if class is not going to happen because of that. It happened on Sunday and it happened today. For some reason, Spectrum is having issues in this area, at least this week. I've never had a problem with them in the past with these things. Any questions?
I actually have a question, but regarding the homework that's going to be turned in this week.
Okay.
For the problems that we do, are we just able to submit a picture of our like work that we're doing in our notebook?
Picture would be fine as long as you can read it. Please, if you're gonna handwrite stuff, make sure it's readable, or you can actually write it on a Word file or text file or something. Also, you can upload that. So whichever you guys feel about it, that's fine. As long as I can read these things when I'm grading them, that will be fine. Okay.
Okay.
Again,
Thank you.
so that is basically as far as that. Sorry about Man City, the fans of Man City, they lost the other day, okay? I see Marwan is a soccer fan.
Hey, it's okay. Manchester's still blue.
Okay, okay, so they're still ahead, that's fine. Okay, so let me stop the recording.